So welcome back. Now we are going to continue with the new parts on document stores. So I need to tell you the motivation of that. So you know that in the beautiful world of SQL, we have relational tables and the rows are flat and we have the same structure in every record. And in that beautiful world, we have the relational algebra, which allows us to project, select, join, group, sort on relational tables, right? So we've rehearsed that in the first week of the lecture with the SQL brush up. Because we saw that there is a syntax called CSV that allows you to store that kind of things. We can use the SQL language. By now you all know it, in order to query relational data. In fact, we saw SQL again with data frames. So we can even use SQL with data frames. And in terms of stack, how are we doing? Wow, we are doing well. So this is what we've done with relational tables. So we can store CSV files on HDFS, encode syntax CSV. We can have even data frames. I can even nest a few things in there if I want to break the first normal form. I can also validate if I have a schema. In fact, I can even defer the validation. Like after, I can store it unvalidated in CSV, then validate later. Then I can process it with Spark. In fact, with Spark data frames, you can easily open the CSV file as a data frame. It's going to validate it for you. I can even store that data in tables if I want. Maybe I can use HBase for that. And that's even better than storing it as CSV, right? And for querying, I have SQL. So in fact, we're doing quite well for relational tables. Indexing, we'll see it actually in this lecture a little bit. User interfaces, this is not a ChatGPT lecture, but this is the future, right? But I guess ChatGPT will still be using SQL in the background to get strong and robust data sources. All right, what about trees? Because you know that denormalized tables are actually trees. Who says tree says XML JSON in terms of data models, which just doesn't mean you will physically store it as XML and JSON, but it's the idea, right? We have collections of trees. How did we do? Well, quite well, but a bit less well, right? We didn't do everything. We covered storage, encoding, syntax, XML, JSON, data models. We have trees, validation. We have XML schema, JSON schema. You know how to validate data. You even know how to create data frames if it's structured enough. We know how to process them with Spark. What we don't know what to do is, however, have a data store for collections of trees. That we haven't seen. What we saw is a Delta Lake for collections of trees, because I just dump my XML and JSON on top of a data lake, right? A data lake is S3, HDFS, Azure Blob Storage. You can call that a data lake, right? So you can just dump your data in there and that's it, right? But that doesn't make it a data store, right? So we will dive into what it means to be a data store. We also don't have a query language. What we have is a query API, right? For that, we have a query API in Spark to process RDDs. We kind of have some sort of Spark SQL that allows us to query collections of trees, but I already pushed it a bit to the limit, right? I explained to you why. If it's simple enough, that's fine. You can use Spark SQL with data frames, with nestedness. But as soon as you're going to have more nesting and more complex data, you will notice that Spark SQL is going to give you headaches, right? You can do it, but it's going to be a bit involved, right? So we are not quite done yet in terms of query languages. So now, in the case of relational database, we have our stack, relational schemas in PostgreSQL, queryable tables, and so on. And now we are going to be looking into semi-structured stacks. Semi-structured is just another word for denormalized data or collections of trees, right? There is a difference here that you might have noticed between the two slides here. And the difference is just that if we have relational tables, it's always validated. We always validate data. Why? Because I have a guard at the door that checks that any data you put in there is going to be valid against the schema. But when you have semi-structured data, you delay the validation. You store the data, it might be not validated yet, you just do it later, right? Maybe schema on read, when you read the data, you can test the validation. So this is why the validation is kind of optional in this stack. So this is the difference. And the other difference is obviously trees instead of tables, right? Okay, now a common thing that database scientists love to do when they have a new shape of data is they try to take a hammer and fit it into another shape. And so, as you might imagine, people have tried to take the collections of trees and force fit them into tables. So can we take a hammer and hit the collections of trees hard enough that they will just fit in a relational table? People have tried it. Doesn't quite work. Well, it does work, but it's not always working as well as one might think. In simple cases, it works. If I take a flat JSON object that's in the first normal form, and that I can force fit into some row, right? You agree with that, right? If I give you a flat JSON object, I can put it in a row like that. So that is the easy part. If I have XML like that and it's flat, I can also force fit it into a record, right? But this is easy. This is because I have a very specific kind of XML and JSON in here. What about two trees? Now I have two trees. Who sees trees, by the way? Almost all of you. That's awesome. So you follow the data modeling lecture. But these are flat trees. These are flat trees, and they have the same structure. Look, they have exactly the same elements, the same types, and so on. So I can actually fit that into a nice table with two rows, right? Who sees it? Right? I can take these two trees and fit them into tables. But again, it worked because it's very specific. I have flat documents that look the same. This is why it works. I can even make a schema for this. For this document here, I can have this XML schema. All I need to do is specify the name of my elements and the types that are attached to them, all atomic types, because that's in the first normal form, atomic integrity. And actually, I can even take the XML schema and find the corresponding SQL schema, right? So the SQL schema, that's your create table statement in SQL, right? That would be your schema. So I can even turn that into a relational schema where I have the name of my columns and the types of my columns. But again, why does it work? Because here I'm not nesting anything. I just have a flat schema with just known columns that are not even repeated. I don't have any min occurs, max occurs in there, just once each, and I have a type. Okay, the same goes for JSON. I can also convert them to schemas if it fits like that. But here's the problem. This is only a special case, because in general, when I have collections of trees, they might be nested. That's the first thing. They can be nested. But on top of that, they can also be heterogeneous. It might be that I don't even have any schema, or I have a very loose schema that is very permissive for extra fields and absent fields and so on. So basically, I'm breaking two rules. I'm breaking the atomic integrity, the tabular integrity. No, I'm breaking all three rules, in fact. So you see, I'm just completely outside of the relational algebra kingdom in that case, right? So it means that if I want to convert into tables, when it's heterogeneous and nested, that's going to be tough, right? It's not going to be just a smooth ride like this. People have tried it again in some cases. If you have a schema, like if I give you this sort of documents that contain nested tables, arrays of objects that look alike, that's nested tables, I could use all of what I learned in my bachelor's of computer science in database systems. I know how to normalize it into the first normal form and even higher normal forms by splitting it into several tables. So I will find a way. But why do I find a way here? Because I have a schema. See, even if you don't have the schema, you see the schema, right? It's the same structure everywhere here. Both at the top level in yellow and at the second level in purple, you have a schema. This is why you can actually still figure out a way of building the tables. But that way is going to be different for every schema. You have to do the same job every time you need to convert it. The problem is that if you have heterogeneity, because your schema allows for missing keys, for example, you kind of still squeeze it into a table in a way that works. You're just going to have nulls all over the place. So already here, you can do it. You can have nulls in a relational database. But if you have a lot of nulls, you're going to be inefficient, right? Because a relational database is not meant to be used with nulls at a lot of places, right? And not to mention the number of columns you might get with plenty of nulls. That's absolutely not what a relational database is built for. So there is what we call here an impedance mismatch. An impedance mismatch is when you try to force fit with a hammer a square peg into a round hole. And in fact, this is exactly when we try to fit collections of trees into tables. This is what we are, in fact, doing. People found ways, actually, there are academic papers with generic mappings from trees to tables. There's even one that manages to store an entire collection of trees in a single table with few columns. I'm amazed at how brilliant this is. The problem is that it works, but when you look at the table, no human can ever decipher that. This is just some sort of mathematical function that preserves all of the information and fits it in there. You cannot, as a human, immediately see the data as easily as if you look at XML or JSON. So this is what I mean with a square peg into a round hole. We can try. It's a good idea in some cases, but generally we cannot just reuse a relational database. That just doesn't work. We need to invent something new that would natively support collections of trees in a way similar to PostgreSQL. nth document store. So what is going to happen? We are going to build a system that is a bit like PostgreSQL, in the sense that it's a database system that stores data that you can query and blah, blah, blah. And the way it works is that I'm going to be supporting what's called a document, but in fact, a document is a tree, right? Because I say JSON document, XML document. So this is why it's called document store. I could have called it a tree store also. That would have been fine, right? But basically, I have collections of millions or even billions of documents. This is the equivalent of the relational table in PostgreSQL or in any relational database. In a document store, I have collections of documents, collections of trees. Now, in the specific case that the trees are flat and homogeneous, technically it's isomorphic to a relational database, in which case I should not be using a document store, I should be using PostgreSQL, right? But technically, this is a superset of what PostgreSQL can do, right? And by the way, what I said about the fact that if your trees are flat and structured, you should be using PostgreSQL, take that seriously. Too many people use document stores when they should be using a SQL database system, because a relational database system is going to be much more mature and bring you more guarantees, right? All right, but if your data is nested or heterogeneous, then document stores are for you. So with documents, I mean that, and literally XML and JSON, there are XML document stores with collections of XML trees, and there are JSON document stores with collections of JSON trees, and they exist. I will show you a few examples. So what that means is that in a collection, in a JSON document store, I have billions of objects in a collection. In that case, of course, my screen is too small, so there's only 3 objects here, 1, 2, 3. And they kind of look alike. I have foo with an integer, bar with, oh, it's heterogeneous. Here it's a string in the middle, it's an array in the first and third. So you see, you couldn't fit it so easily into a relational database. In a document store, no problem. No problem at all. You can actually put that in a document store, no questions asked. It works. So that's the benefit of a document store. As a rule of thumb, what happens is that when we have these collections of trees, there are a few rules of thumbs about what we are doing, because collection of trees is very generic, right? What I should have said is huge collections of small trees. This is what we're talking about here. Typically, the trees are going to be reasonably small. Remember that they would correspond to a record in a relational database, the trees, right? If they were flat. So the trees should be relatively small. Typically, as a rule of thumb, many systems limit it to 16 megabytes. That's already a lot, 16 megabytes, right? But basically, you cannot have a document larger than 16 megabytes, right? However, the number of documents, that's, you can go crazy, right? So billions, trillions, even if you have larger systems nowadays. So a huge number of small documents. A small number of huge documents, no go. That's not what you use document stores for. All right. In fact, the size of a document has an order of magnitude. You can, in your mind, put it in relation with the cell of a white column store. Big table, right? You can put up to 10 megabytes in one cell. That's the same order of magnitude. So in HBase, you can put JSON documents or XML documents in the cells of your HBase system. And here it's just linear. So in HBase, you would have a 2-dimensional table of that. Here it's just linear. You just have a collection of documents. But the size of them, it's the same order of magnitude, 16 megabytes, 10 megabytes. That's the idea, right? And again, it depends on the system, right? It's 16 megabytes for some systems, 64 megabytes for some other systems. There are systems that will not even put any limits to you, but if you try it, it's just going to be slow. So maybe they are not, it's not really giving you a service to you to actually allow you to be larger than that, but that's the idea. All right, so typically small documents and thousands, millions, billions, trillions of documents in a collection, a huge collection of small trees. Again, that I'm just repeating myself. the special case in which the trees are flat, this is when we don't have nestedness, but document store also allows for nestedness. And there is the specific case where the trees are homogeneous, but there can absolutely be heterogeneous, and that's fine too in the document store. But these are the two dimensions and the two ways to break the rules of the relational model, basically, by being not flat and by being not homogeneous. But you do have cases in which you have a document store with nestedness but homogeneous, and you can have a schema. In fact, that's called the data frame. And you also have the case where you're flat, but you're heterogeneous, right? So these are specific scenarios. And then there are the cases where it's both nested and heterogeneous. That is where you break the two rules basically at the same time. All right. So now what can we do in a document store? Well, the good news is that a lot of the things we can do are very similar to the sort of things you can do in a relational database. So it shouldn't surprise you when I say that we can select document, we can project document, we can aggregate documents. No, actually, we cannot join documents. Joining in many document stores is not allowed. Why is that? Well, because it's expensive. Because another aspect is that, remember that the reason we have trees is that we denormalize the data. You might remember that denormalizing the data means that you pre-compute the joins. You basically create the nestedness with the join. So the joins are technically superfluous if you already nest the tables in the tables. Then you don't need joins anymore. So that's the spirit of not needing joins. Now that's the theory. The practice is that people re-implement the joins in C++ or Java on top of the host language of the document store, which technically shows that we're not quite there yet. The fact that people still need joins and re-implement it themselves, all you did is push the burden of that to the user of the system, all right? But just as a rule of thumb, again, many of them will not support the joins. Now, another aspect of a document store is that you can defer the validation for later. You can create a collection without any schema, totally fine. You can even dump absolute heterogeneous data in there, that's totally fine. But if you want, you can also specify a schema, and then the document store is going to check the schema, the validation, the validity against the schema for every tree that you try to put in the collection. You have the choice, right? Either you want a schema or you don't want a schema. All right, you can even do it on the fly in some systems. Okay, now there are plenty of systems like that, right? Just like there are many relational database systems like PostgreSQL, IBM, Oracle, Microsoft, and so on. They all have theirs. Well, it turns out that document stores also have plenty of products. Who heard of at least some of them? Right, many hands, right? So we have MongoDB, CouchDB, Elasticsearch, ExistDB, CloudEnt, ArangoDB, MarkLogic, Microsoft Azure, BaseX, and so on. First, anything that has an X is basically an XML document store. That's the way you market these products. So ExistDB is about collections of XML documents. BaseX is about collections of XML documents. The only exception of MarkLogic is that although they don't have an X in there, for some reason, it's still XML documents in there. Although I think MarkLogic also added JSON support and even graphs, I think now. MarkLogic is probably the oldest enterprise-ready of these products, right? It was actually in the news back then after a healthcare reform in the US because the system was actually built with MarkLogic. All right, but there's plenty of new ones. MongoDB is JSON, Elasticsearch is JSON, CloudEnt is JSON, ArangoDB is JSON. CouchDB is JSON. Microsoft is pretty much everything. They like to have systems that support many different data shapes. I think it was called the Polystore or something by some of the famous engineers there. But this is basically the landscape of things. Just a word of warning, Elasticsearch should not be relied upon as a storage. It's meant to index your data, for example, for full text indexing, but do not trust that system for durability. It's not meant for that, right? It's official, right? It's not like I'm criticizing. This is just not a product meant for storage. This is just meant for easy retrieval, but that should be a copy of data that you store elsewhere. All right, and the one that we are going to focus on is MongoDB. But again, if you learn about MongoDB, you will be able to very easily learn any one of the other systems. Who heard of MongoDB? All right. The first time they were in the news, I think it's because they raised $1 billion of financing, and now they grew bigger, and they are still here today, right? Okay, so I'm going to take the example of MongoDB, but again, keeping in mind that this is generic. Now, I'm coming back to something that I've already told you. The systems globally can be classified in two categories. There are the data lakes, where you just drop your data on some file system. That's what we did with HDFS or S3, that we read with Spark, Hadoop MapReduce. In fact, when you use Python and Pandas, it's the same, right? You drop your files on the drive, and then you read them in this way. So this is the data lake approach. And we've been using it in several weeks, actually, because we spent time on MapReduce and Spark. But now, just for today, for the document stores, I'm walking back to the light side of the force here with databases where you import your data first. Like PostgreSQL, you need to import your data before you can use it. This is called ETLing. So MongoDB, in that respect, is closer to PostgreSQL than it would be to Spark or even Spark data frames. So this is just to think as an equivalent of PostgreSQL. Now, there is a benefit to having a system on the light side of the force, on the ETL-based systems, is that the system is free to store the data in any way it wants, because anyway it's hidden from the user, right? I don't know if anybody knows how PostgreSQL stores the data. You're not supposed to know, in fact, and you shouldn't care, because maybe they even change it in every version. What you do care is how you interact with it. That's called data in the, wait for it, dependence. Yes, data independence. Okay, well, in the case of MongoDB, they, of course, are not going to store it as text. That would be very inefficient. They are using a binary format that's called BSON. And in fact, you can find it, I think, bson-spec.org is the website, if I remember. And it's just a way of compacting any JSON representation as a string of hexadecimal numbers, in other words, a binary file. You don't need to know how that works. I just put an example right here that basically says this is the beginning of an object. This is a string, this is FFO, this is and so on and so on, right? So you encode it, taking much less space than it would be in text, right? So the idea is you import your JSON, and then MongoDB stores it in this way, but you don't need to care about it because it's all hidden from you. The second aspect of a document store, like MongoDB, is that it's actually not as high level as a full-fledged relational database like PostgreSQL, in the sense that it gives you a basic API to create documents, read documents, update documents, delete documents, not as high level as SQL. In a way, you can relate that to HBase to some extent, even though that would be slightly on a higher level than HBase, right? HBase has get, put, scan, delete, so you could actually compare this in this way. It's called CRUD, C-R-U-D, create, read, update, delete. So if you see CRUDs, that's basically the abbreviation of that. Okay, so the bad news I have for you is that, at least for now, but we will see next week, we'll solve that. I'm not going to have any language like SQL just yet. Why? Because it doesn't exist in MongoDB. And in many document stores, it doesn't exist. Some of them now have a query language. So what I can give you, however, is an API. In that case, it's a JavaScript API. There is also a Python API available. It's not as good as a query language, but it does the job, right? So it's already a way of interacting with the database. And the idea is that the people doing that are actually programming in Python or Java or C++, more complex code that interacts with MongoDB in this way. This is how it's meant to be used, okay? So typically, it's a backend behind a website or something like that, and you interact with it through this API. So I'm going to teach you a bit how this API looks like, just to give you an impression of the sort of things that it can do and how it supports nestedness and heterogeneity, because that's the whole deal here. What I'm going to do is to help the learning. On the top right, you see this little box in here that I added, which is, I call it the SQL cheat sheet. It's kind of a SQL equivalent of what we are doing, but it's only meant to be given as a general hint to visualize, to map it to SQL. It's not always going to be possible to do that because, again, it's more generic than SQL, but it just gives you an idea, right? So it's just to help you to learn. But again, I repeat, SQL is not supported by MongoDB. even though I imagine that people put connectors on top that might automatically convert SQL queries to this, but not in the core MongoDB. All right, so the first thing is, if I have a collection called scientists, and I want to list it, that would be select star from scientist in SQL, then I have in JavaScript DB, it's always DB, dot the name of the collection, scientist, dot find. And here I can either give no parameter at all, or I can pass an empty object. It's the same thing. That gives me the entire collection, right? In practice, if it's too large, you're just going to iterate, because again, you're interacting with Java or Python, right? So you can imagine a for loop, and then you go through all of the objects that are returned, right? Something I'm not showing on the screen is that there is an additional key in all JSON objects that is added automatically if you don't have it when you populate the data. It's an underscore ID field. It's just some sort of object ID that is automatically assigned to any object in a collection. It's native to MongoDB. It will do it for you. Just to not bother you with that, I don't put it on my screen, but if you interact with MongoDB, you will see some underscore ID with some weird binary value appear. That's just an object ID, right? It uniquely identifies every object. Okay, now let's go with selection. How do I select documents that match a criteria? Let's do the equivalent of a select from where with an equality. Theory is relativity. The way I do that is that I pass to my find function an object that corresponds to what I'm looking for. So here I'm looking for theory equals to relativity. So I'm just putting that JSON object, theory relativity. And that gives me a selection criteria that in that case, if I have a collection of these 4 documents, it's returning the first and the fourth document because they both have theory relativity. For whom is that clear? All right. So again, the idea is it's not a language like SQL. We just use some sort of JSON syntax to show by example what you're looking for, and that acts as your selection criteria. Okay. How do I project? So that would be the equivalent in SQL of select first last. So if you add a projection in there instead of the star, well, that is a second parameter to the find function. So the first parameter is a selection. The second parameter is a projection, right? How do I project? Well, I just put as the keys all the fields that I want to project to, the one that I would put in the select clause in SQL, associated with the value 1. 1 for I want it, right? So first and last, first is 1, last is 1, and then I end up with this query with the 2 objects that are shown here, with only first and last appearing, right? In practice, you're going to have the underscore ID that is always included, but again, I'm not bothering you with the underscore ID, right? For whom is that clear so far? Right, so first parameter, selection, second parameter, projection. Now you already probably start getting this itchy feeling that this is not a query language, right? Because you need to write a JSON object, first one, last one, sounds a bit arbitrary. That's because it's an API, right? There is a documentation that you can read that tells you how it works. And you see that it's going to become a bit more complex as we make progress. Now, something I cannot do with SQL, and now we start seeing the benefits of a document store, is projecting away. Now, I don't want to project to specific columns. I want to remove specific columns. So it means that theory 0 instead of 1 means I want everything except theory. You cannot do it in SQL. SQL doesn't give you a way of doing something like that. You would have to manually list the columns you can include, but you cannot do something like remove. And again, in the case of SQL, it's no big deal. You know the schema anyway. So it's always possible to get the columns that you want to keep. But in MongoDB, it's not the case. You don't have a schema. You might not know all of the columns that you have. You might have 1 trillion objects. You might have plenty of extra columns. So in that case, you want to just project away, not knowing the other columns. Now, how do I have an end? If I want to select for 2 equality criteria, then I just add them in my JSON object. It's meant as an end. So here it's meant as theory relativity and last equals Einstein, as you can see in the SQL equivalent. That's going to return the same, the first document. So that's great. That's the end. The problem is the or. And now you start seeing the limits of having an API, not a language, is that now, in order to say either this or that, I need to use special fields, special keys that start with a $. And what I need to do in my JSON object is a $OR as a key with an array, and then I list the criteria that I want to OR, to have a disjunction about, right? So now it's either Newton or Einstein, and I get the first two objects. You see, in SQL, it's much easier. You just swap the and for an OR. But in the API, it's not that obvious between and OR. It's really, you start seeing that it's becoming complex. Who is with me, right? Who feels that this is adding complexity here, right? And for the projection. All right, that's the good intuition. All right. Now, what about not equality, but inequality? I can do it greater than or equal $GTE, and then I can have this where publication greater than or equal to 100 in SQL. And I have publications object GTE 100, right? Now you start seeing it's really not very convenient. It's an API. Again, it's an API, not a query language. And the Python API might be slightly different, right? So just be prepared for that. Okay, and now you see I have 500 and 400s that I managed to catch. Now, what about heterogeneity? What if my collection doesn't have the same fields everywhere? Well, that's okay, because what's going to happen, for example, if you're looking for theory relativity and one of my objects doesn't have any theory field, which is fine, it's a document store, then that's just not included in the results, right? I have theory relativity, it's just leaving that one out and only outputting those that have it, but it's not going to throw an error. How do I specifically look for those that have a missing theory with null? I use my JSON null with theory null. That basically means it returns the fifth one. Now, what's going on here? For MongoDB, it's the same thing to associate a key with null or for the key not to be present. It basically considers the two equivalents. That's the reason. If you had theory null, which you could have in the data, it would also be returned, right? You cannot distinguish between the two. So you need to be aware of that because there are systems that distinguish between the two, and we did distinguish in JSON, but in MongoDB, it doesn't distinguish. It's equivalent to be absent or to be null. So this is why it works in this way. What about nestedness? Again, let's go to what SQL cannot do, right? So what about this query? What I'm doing here, find name dot first Albert, where just like the $sign, the dot is also special. And in fact, what it does is navigates. Name dot first means I have an object name, and nested in there, I have a key that's called first, and name dot first filters for that. So I'm returning document 1 and document 2. Who agrees? Right? Name dot first. So the dot is special. If you want to catch a field that is actually called name dot first, you will need to escape. So there are escaping mechanisms that escape the dot in order to make it, to avoid the interpretation as nesting, right? Now, many people do this mistake. They want to look for the objects with name and then nested first Albert, and they do this. It doesn't work. Why? Because when you do this, it looks for equality of the entire object. It's going to return this, which is exactly the same object, but it's not going to return that. That might be a mistake that you might be doing at the beginning. And again, you should be using the dot if you want to also return that. Okay, so this is a common mistake. This is really checking for exact logical equality on the object. Now, what about arrays? It's also going, if you have an equality like that, but it turns out to be an array of strings rather than a string, this is also going to go inside the array. So if you have an array of strings, theory special relativity will also return this, right? And now you need to be careful about that because this behavior is arbitrary. This is a design decision of the MongoDB developers. It's in the documentation. Another product might use a different convention, right? So you start seeing the limits of an API, right? The API, it's very intuitive with simple queries. As soon as you want to do more complex things, it's going to be more involved, and you're going to spend a lot of time reading the documentation for these things, right? All right. You have other dollar operators that are very convenient. For example, $in allows you to check if a value is within a set of value, for example, either ETH Zurich or EPFL. You could have caught it also with the $or, by the way, it would have been fine, but this is maybe a bit more compact to write with the $in. We also have the little sister, $nin, which is not in, so basically now it excludes the universities that would be ETH Zurich or EPFL, okay? Okay, so that's for the finds. Outside of the finds, we can do other fancy things. For example, I can add a dot count, right? I can count the number of objects that are, in that case, passing that filter, right? And that gives me a number. I can sort. If I iterate through the results, I can sort them with my criteria. -1 means decreasing, 1 means increasing. That would be the equivalent of ask and desk in the order by clause of SQL. And I even have skip and limits, but that shouldn't surprise you. It's like the offset and the limit and offset of SQL, right? So it shouldn't be any surprise, but there is basically this way of doing that in MongoDB. One thing to pay attention to is that I can actually put them in any order. I could have skip and then sort and then limit. It doesn't matter. This is not an imperative API. It's a functional API, right? So the order in which you put them has no impact on the results. So that's also a common thing that many do not realize. Okay, you can eliminate duplicates with all distinct values of lasts and so on. And finally, you have aggregation pipelines. What does that remind you of? This thing right here. I merge, then I group, then I sort, then I limit. Doesn't it remind you of something? What did we see last week and the week before? Apache Spark, right? This is Spark. Look. Creation, transformation, action stages. That's the reason I'm not going to even talking about that. You can basically have an API that's kind of support a similar way of doing things. But since you've already learned Spark and MapReduce, you will have absolutely no difficulty going into this API. But we'll see a much better way next week with the JSONic language that is just like SQL. All right, this is where I stop for today. Just before you go, if I manage, I want to check how much you've been following, just like this. Okay, so just let me know before you go. Wait. You need to let me, don't go just yet. Don't go just yet. I need to find the date. Yeah. So thank you very much for attending this lecture. We'll continue tomorrow at 9 a.m. with document stores. We'll take it from there. I'll take time to answer any questions you might have. Wonderful, majority over 80%. Thank you very much. Have a nice evening.